Now, in this lecture, we'll find out the radius of a circle using two different methods. In the drawing, we have a circle. Inside the circle, we know that the center of this circle is at this point O. We also have inside the circle line segment AB that is equal to 6 units in its length. We have line segment AD that is equal to 18 units. And finally, line segment BC equals to 13 units. Angle DAB, this angle equals to 90 degrees, and angle ABC equals to 90 degrees also. Our mission is to find out the radius of this circle. So, first of all, we'll make a construction from point C. We will draw perpendicular on AD. Again, from point C, we will draw perpendicular on AD. So actually this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point C and AD as E. So by doing this construction, we can get quadrilateral ABEC. Inside the quadrilateral ABEC, we have 1, 2, 3 right angles. The sum of 3 right angles is 90 times 3. It is equal to 270 degrees. Plus the missing angle here. In total, the sum of the angles in quadrilateral ABEC must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle here must be equal to 90 degrees. In order to complete the sum of the angles in this quadrilateral to 360 degrees, the missing angle must be equal to 90 degrees. So actually inside quadrilateral ABEC we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral ABEC as a rectangle. But we know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to EC. But AB equals to 6 units, therefore EC must be also equal to 6 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that BC equals to AE. But it is given as the equation that BC equals to 13 units, therefore AE must be also equal to 13 units. Okay, what is the length of line segment ED? The length of line segment ED, it is very easy to see that ED equals to AD minus AE. Again, ED equals to AD minus AE. This is to say, ED equals to AD that is 18 units minus AE that is 13 units. 18 minus 13 is 5. So found out that ED equals to 5 units in its length. In the next step, we will join points C and D together by a straight line. By joining points C and D, we actually created the right triangle ECD. So we will implement the Pythagoras theorem on the right green small triangle ECD. Here by PT is evaluation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the green triangle is DC. Therefore, the square of the hypotenuse is DC square. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EC square plus ED square. So, in conclusion, we found out that in the right green small triangle ECD, according to the Pythagoras theorem, DC square equals to EC square plus ED square. So DC square, that is the square of the hypotenuse, equals to EC square. EC equals to 6, therefore EC square equals to 6 squared, that is 36. Plus ED square. ED equals to 5 units, therefore ED square equals to 5 squared, that is 25. So in conclusion, we found out that DC square, that is the square of the hypotenuse, equals to 36 plus 25. 36 plus 25 is 61. So DC square equals to 61. We will take root out of this equation, and we get that DC, that is the length of the hypotenuse, equals to the square root of 61. Okay, DC equals to the square root of 61. You can write here that DC equals to the square root of 61. In the next step, we'll join points B and D together by a straight line. By joining points B and D, we actually created the right triangle ABD. So we will implement the Pythagoras theorem on the right triangle ABD. Again, by PT is evaluation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle ABD is BD, therefore the square of the hypotenuse is BD square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AB square plus AD square. So in conclusion, we found out that in the right triangle ABD, according to the Pythagoras theorem, BD square equals to AB square plus AD square. So BD square, that is the square of the hypotenuse of the right triangle ABD, equals to AB square. AB equals to 6, therefore AB square equals to 6 squared, that is actually 36, plus AD square. AD equals to 18 units according to what is given us the question, therefore it is 18 AD square, it is equal to 18 squared, that is 324. So in conclusion, we found out that BD square, that is the square of the hypotenuse of the right triangle ABD, equals to 36 plus 324. 36 plus 324 is 360. So BD square equals to 360. We'll substitute 360 by 36 times 10, and we'll get that BD square equals to 36 times 10. Here we will take a root out of this equation, and we'll get that BD, that is the hypotenuse of the right triangle ABD, it is equal to the square root of 36 times 10. The square root of 36 is 6, so we'll take 36 out of the root. And we'll get that BD equals to 6. Inside the root, we're left only with 10. 6 times square root of 10. So the hypotenuse BD is equals to 6 times square root of 10 units. Okay. In the next step, we'll find out the area of the triangle BDC. Okay, so we'll find out the area of the green triangle BDC. The area of any triangle, and especially the area of triangle BDC. Here, the squared brackets is the sign for the area. It means the area of triangle BDC will be equal to the base of the triangle times the height to the base over 2. Here I must emphasize that the height to the base must create 90 degrees with the base. Okay? So the area of triangle BDC equals to the base times the height of it over 2. We will choose the base of the green triangle BDC as BC. So we substitute the base by BC. Times the height over 2. So again, the height must create 90 degrees with the base BC. So therefore we actually must extend the base BC, and from point D, that is the vertex of the green triangle BDC, we will draw perpendicular on the extended BC. So actually this angle equals to 90 degrees, and this angle it is also equal to 90 degrees according to our construction. We will define the tangent point of the perpendicular from point D and the extended BC as F. By doing this construction, we actually created here quadrilateral ABDF. Inside quadrilateral ABDF, we have 1, 2, 3 right angles. 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay? So I actually found out that quadrilateral ABFD, the big quadrilateral, has 4 right angles. Therefore, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate quadrilateral ABDF as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to DF in rectangle ABDF. AB equals to DF. AB equals to DF, according to the rule that the opposite sides of a rectangle are equal to each other. But it is also given us the question that AB equals to 6 units. So we can write here AB equals to 6. And from this equation, 6 equals to AB equals to DF, we will derive that DF is also equals to 6 units. Now DF equals to 6 units, and DF, it is actually the height. Why DF is, it is the height to the base, of the extended BC, because of the fact that DF, line segment DF, creates 90 degrees with the extended BC. Okay, and therefore now we can find out the area of the green triangle BDC. So the area of the green triangle BDC equals to the base that is of the triangle that is BC, but we know that BC equals to 13 units, so it is 13 times the height to the base. We just right now found out that the height to the base is df, that is equal to 6 units over 2. So the area of triangle, the green triangle BDC equals to 13 times 6 over 2. Here 6 over 2 is 3, and 3 times 13 is 39. So in conclusion, we found out that the area of the green triangle BDC equals to 39 square units. Okay? In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. This will be rule number 1. So if we have a circle, that could be any circle, this is the center of the circle. Here, point O is the center of the circle, and inside this circle we have a triangle that is blocked by the circle. Here, triangle ABC is blocked by this circle. This is triangle ABC. We actually know that the length of side AB equals to A units, side BC equals to B units in its length, and side AC equals to C units in its length. Again, point O is the center of the circle. And the radius of this circle is equal to capital R. So here, from the center of the circle, we draw the radius, touches the circle at point M. Here OM is the radius of the circle, because it starts from the center of the circle and ends at point M, that is the point of the circle itself. This is exactly the definition of a radius, therefore OM is the radius of this circle, that is equal to capital R according to our definition. Okay? So this is actually the drawing of rule number 1. So according to rule number 1, if a triangle, that could be any triangle, or so, or you can say that if a triangle ABC, here this is triangle ABC, but triangle ABC could be any triangle. So if a triangle ABC that could be any triangle is blocked by a circle, this circle blocks the triangle, I will explain what is the meaning of a triangle that is blocked by a circle. Actually, a triangle is blocked by a circle only and only if all the three vertices of the triangle are touching the circle. Like in this drawing, you can see here that this vertex of the triangle touches the circle at point A. Likewise, this vertex touches the circle at point B, and finally this vertex of triangle ABC touches the circle at point C. Only if all the three vertices are touching the circle at different points of the circle, only then you can say that the triangle is blocked by a circle. Okay? So if a triangle ABC is blocked by a circle, like in this drawing, then the radius of this circle, then the radius of the circle that blocks the triangle like in this drawing, this circle blocks triangle ABC will be according to the following formula. Here we define the radius of this circle as capital R. It will be equal to A times B times C. This is actually the multiplication of the side lengths of the triangle by each other. The length of side AB is A, the length of side BC is B, and the length of side AC is C. So it is A times B times C over 4 times the area of triangle ABC. Okay? This is the small brackets is the sign for the area. It means the area of triangle ABC. So we actually can implement rule number 1 in our drawing. Why? Because of the fact that the green triangle BCD is blocked by this circle. Why it is blocked by this circle? Because of the fact that this vertex touches the circle at point B. This vertex touches the circle at point C, as you can see here. This is point C. This is the touching point of the vertex with the circle, and finally this vertex touches the circle at point D. Point D is the touching point of the vertex of this triangle with this circle. Therefore, definitely we can say that indeed the green triangle BDC is blocked by this circle. So I write it down. The green triangle BDC is blocked by a circle, this circle, Whenever you have a triangle that is blocked by a circle, you can implement rule number 1. Therefore, we can implement here rule number 1. We will define the radius of this circle as capital R. So here, point O is the center of the circle, point M is the point on the circle itself. Therefore, OM is the radius of this circle that is equal to capital R according to our definition. So, therefore, here we will implement rule number 1. Therefore, according to rule number 1, the radius of the circle that blocks the green triangle BDC will be equal to the multiplication of the sides length of the green triangle. That is actually BC is the length of this side times DC is the length of this side of the triangle times BD is the length of this side over 4 times the area of the green triangle BDC. Repeat again, the area and the radius of the circle, of this circle that blocks the green triangle BDC will be equal to the multiplication of the side lengths of the triangle by each other, that is to say it is BC times DC times BD over 4 times the area of the green triangle BDC. So capital R equals to BC. BC equals to 13 units, according to what is given as the question, times DC. We have already found out that the length of side DC of the triangle BDC equals to the square root of 1 units times BD. The length of side BD of the green triangle BDC, it is equal to 6 times square root of 10 units. All divided by 4 times the area of triangle BDC. And we have already found out that the area of triangle BDC equals to 39 square units. Here we will simplify this expression by dividing both the numerator and the denominator of this expression by 13. So capital R, it is equal to 13 over 13 is 1, so 13 will get cancelled, and we left only with square root of 61 times square root of 10 times 6 over 4 times, and 39 over 13 is 3. So in conclusion, we found out that the radius of the circle that blocks the green triangle BDC is equal to the square root of 61 times square root of 10 times 6 over 4 times 3 is 12. The denominator we have left only with 12. Here we divide both the numerator and the denominator of this expression by 6. So capital R, that is the radius of the circle that blocks the green triangle BDC, will be equal to the square root of 61 times square root of 10, and 6 over 6 is 1, so 6 will get cancelled. In the denominator we have to divide the denominator 12 by 6. 12 over 6 is 2. So in conclusion, we found out that the radius of the circle that blocks the green triangle BDC equals to the square root of 61 times the square root of 10 over 2. Here, according to the algebraic identity, the square root of A times square root of B equals to the square root of A times B. We get that the square root of 61 times the square root of 10, according to this, to the trigonometric identity, will be equal to the square root of 61 times 10, all divided by 2. So the radius of the circle that blocks the green triangle BDC will be equal to 61 times 10 is 610, so under the root we have 610 over 2. Again, the radius of this circle that blocks the green triangle BDC will be equal to either the square root of 610 over 2 units, so in terms of numbers it is equal to 12.349 units. Okay, so we finished with the first method. In the next step I will present to you the second method. The second method, how to find out the radius of this circle, that is the radius of this circle. Actually this circle, it is also blocks the triangle BDC. In the second method, in the first step, we do actually the same thing that we did in the first method. That is to say, from point C we go perpendicular on AD. And this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and ADS. Yes, we did in the first method. Here, I'll not repeat on the same thing that we did in the first method. This angle equals to 90 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, quadrilateral ABEC is a rectangle. The opposite sides of rectangle are equal to each other. That is to say, AB equals to EC equals to 6 units, and BC equals to AE, that is equal to 13 units, and here ED equals to AD minus AE, that is to say it is equal to 5 units. So until now we did all those things in the first method. Now in the second method, from point O we will draw perpendicular on chord BC. So that is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point O and BC as capital N. We will define the touching point of the perpendicular from point O and AD as M, or capital M. In the next step I will present to you A new rule that will be actually rule number 2, and we'll implement rule number 2 in our drawing. Here rule number 2 is true in any circle, so here the circle that I will draw could be any circle. Here point O is the center of the circle. Here chord BC, this is chord BC, could be any chord in the circle, and from the center of this circle, that is to say from point O, we will draw perpendicular on chord BC. So actually this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to our construction. We will define the touching point of the perpendicular from point O and BC as M. So, according to rule number 2, the line segment OM line segment OM, this line segment that exits from the center of the circle that is to say point O, or we can say that the perpendicular from the center of the circle towards any chord of the circle bisect the chord. Okay. So here according to rule number 2, the perpendicular from the center of the circle this is to say the perpendicular from point O, that is the center of the circle, towards any chord. Here chord BC could be any chord. Bisect the chord. That is to say, BM equals to MC. BM equals to MC. Okay. Divide the chord BC into two halves. Each half equals to each other. That is to say, BM equals to MC. This is the first half, and this is the second half. BM equals to MC. So actually can implement rule number 2 in our drawing. Why? Because in our drawing we have the perpendicular ON towards chord BC. I write it down. ON is perpendicular to chord BC. And point O is the center of the circle, so the perpendicular that exits from the center of the circle towards chord BC, according to rule number 2, it bisects chord BC. That is to say, BN equals to NC. BN equals to NC according to rule number 2. Okay? Bn equals to NC. Okay. In the next step, we'll focus on quadrilateral ABMN. In quadrilateral ABMN, this quadrilateral, we have 1, 2, 3 right angles. And therefore, the fourth angle must be also equal to 90 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So, quadrilateral ABMN has 4 right angles, and therefore quadrilateral ABMN is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, AM equals to BN. AM equals to BN. Likewise, we'll focus on the lower quadrilateral MNEC. In quadrilateral MNEC, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees, this angle. And because of the fact that quadrilateral MNEC has 4 right angles, quadrilateral MNEC is a rectangle. And again, we know that the opposite sides of a rectangle are equal to each other. That is to say, ME equals to NC. ME equals to NC. So we can summarize what we did until now. We found out that according to rule number 2, BN equals to NC. But we have already found out that BN it is also equals to AM, so we can write here that BN equals to AM. And we also found out that NC it is also equals to ME. So we can write here that NC equals to ME. So from this long equation, AM equals to BN equals to NC equals to ME, we will derive that AM equals to ME. AM equals to ME. Okay. here AM equals to ME. In the next step, we'll extend line segment AD by a straight line until it touches the circle. We'll define the touching point of the extended line segment AD and the circle as point F. By extending line segment AD, we actually created here chord FD. This is chord FD. This is chord FD. Here, let's see. This is chord FD. And we actually have the old number 1. According to the old number 1, the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on the upper side of the straight line, it will be at point K. Here the sum of those two angles must be equal to 180 degrees. That is to say AKL plus BKL, the sum of those two angles must be equal to 180 degrees. We can actually implement rule number 1 in our drawing. Why? Because of the fact that ON is perpendicular to BC. ON is perpendicular, it is absolutely a straight line. So if we focus on the upper side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees according to rule number 1. So which angles we have at the upper side of the straight line ON at point M? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees according to rule number 1. Therefore, the missing angle must be equal to 90 degrees. Why? Because of the fact that in order to complete the sum of the angles in the upper side of the straight line ON at point M to 180 degrees, the missing angle must be equal to 90 degrees. Okay, likewise, if you focus on the lower side of the straight line ON here at point M, the sum of the angles in the lower side of ON at point M, the sum of the angles must be equal to 180 degrees. So which angles we have at the lower side of ON at point M? We have this angle that is equal to 90 degrees, plus the missing angle. In total, they must be equal to 180 degrees. Therefore, the missing angle must be equal to 90 degrees. Therefore, we actually found out that line segment OM is perpendicular to chord FD. Why? Because this angle equals 90 degrees and this angle equals 90 degrees. And because of the fact that from the center of the circle we have perpendicular to chord FD, according to rule number 2, the perpendicular OM bisects FD. That is to say, FM equals to MD. So I write it down. We know that OM, it is a line segment that exists from the center of the circle, that is to say from point O, and it is perpendicular to chord FD. It's perpendicular to chord FD. Therefore, we can implement here rule number 2. According to rule number 2, OM, it is actually OM, line segment OM that exists from the center of the circle that is perpendicular to chord FD. It is not only perpendicular to chord FD, but it is also bisect chord FD. Okay? That is to say, if OM bisects chord FD, it means that FM equals to MD. FM equals to MD, according to rule number 2. Okay. Fm equals to Md. Why? Because the perpendicular OM from the center of the circle bisects root Fd, and because of the fact that OM bisects Fd, it means that Fm equals to Md. According to rule number 2. Whenever from the center of the circle you draw perpendicular to any chord, that perpendicular bisects the chord. That is to say, it bisects root Fd. It means that Fm equals to Md according to rule number 2. But from the drawing, it is very easy to see that Fm, here Fm equals to Fa plus Am. Fa plus Am. So you can substitute Fm by Fa plus Am, and it is equal to Md. What is the value of Md? It is very easy to see from the drawing that Md equals to Me plus Ed. Me plus Ed. So in conclusion, I found out that Fa plus Am equals to Me plus Ed. But we have already found out that here that Am equals to Me. Am equals to Me, therefore Am and Me will get cancelled because they are equal to each other, and we left only with Fa that is equal to Ed. Fa equals to Ed. Here you can see this line segment Fa is equal to Ed. But we have already found out that Ed equals to 5 units. Here Ed equals to 5 units, according to what we have already found out. Here, this is 5. So we can write here that Ed equals to 5, and from this equation Fa equals to Ed equals to 5, we will derive that Fa it is also equal to 5 units. Fa equals to 5 units. Okay. In the next step, we will extend side BA until it touches the circle, and we'll define the touching point of the extended side BA and the circle as point P. Okay. Here we have the old rule, rule number 2. I remind you the old rule, rule number 2. According to the old rule, rule number 2, if we have chord AB, this is chord AB, that intersects with chord CD, this is chord CD, the intersection point occurs at point O. Whenever you have inside the circle two chords that intersect with each other, like in this drawing, we get that the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We actually can implement the old rule, rule number 2, in our drawing. Why? Because in our drawing we have chord FD. This is chord FD, it intersects with chord PB. This is chord PB. The intersection point occurs at point A. I write it down, chord FD intersects with chord PB. The intersection point is at point A. repeat again. Chord FD intersects with chord PB at point A. Therefore, according to the old rule number 2, we will get that FA times AD equals to PA times AB. And this is according to the old rule number 2. Again, FA times AD equals to PA times AB. FA equals to 5. It is actually AD. This chord is called AD. Again, I repeat again that FA times AD equals to PA times AB. FA times AD equals to PA times AB. The length of chord AD, according to what is we already found out, is equal to 18 units. It is given us in the question actually. AD equals to 18 units. So we substitute AD by 18. And it is equal to PA. PA is the missing 9 segments, so we leave it as it is, times AB. AB equals to 6 units, so we substitute AB by 6. In conclusion, we found out that according to the old rule number 2 that we implemented in our drawing, 5 times 18 equals to PA over 6. Here we'll divide this equation by 6. And we get that PA, the missing 9 segment, equals to 5 times 18 over 6. So PA equals to 18 over 6 is 3, and 3 times 5 is 15. So we found out that PA equals to 15 units. You can write here that PA equals to 15 units. In the next step, I will present to you a new rule that will be actually rule number 4, and we implement rule number 4 in our drawing. According to rule number 4, rule number 4 is true in any circle, so the circle that I will draw here could be any circle. If we have chord AB, this is chord AB that intersects with chord CD. This is chord CD. And at the intersection point, the two chords create 90 degrees between them. That is to say, they are perpendicular to each other. We define the intersection point between the two chords as point O. So I write it down. If chord AB intersects with chord CD and they create between them 90 degrees at the intersection point, at 90 degrees. That is to say they are perpendicular to each other. Here you can see. And the intersection point is at point O. It's point O. This point, we define this point as point E. Point E is the center of the circle. From point E, we'll draw the radius. This is point M. It starts from the center of the circle and ends at point M, that is the point of the circle itself. Therefore, EM is the radius of the circle that we will define as capital R. Then, the following equation is true. So if we know that two chords intersect with each other at 90 degrees, then the following equation will be true. 4 times R squared, again capital R is the radius of the circle, equals to AO squared plus OB squared plus CO squared plus OD squared. Repeat again on rule number 4. According to rule number 4, whenever you have two chords that intersect with each other at 90 degrees, that is to say, when two chords are perpendicular to each other, then the following equation will be true, that 4 times R squared, R is the radius of the circle that contains the chords, will be equal to AO squared plus OB squared plus CO squared plus OD squared. We can implement rule number 4 in our drawing. Why? Because in our drawing, we have chord FD, this is chord FD, that intersects with this chord PB at 90 degrees. You can see that the two chords are perpendicular to each other. They create between them 90 degrees. This angle equals 90 degrees. And because of the fact that we have in our drawing, in our original drawing, two chords that intersect with each other at 90 degrees, that is to say the two chords are perpendicular to each other, we can implement here rule number 4. Whenever we have two chords that are perpendicular to each other, you can implement rule number 4. Exactly like in our drawing. So write it down. In our original drawing, we have chord FD. That intersects with chord PB. This is chord PB, and they are actually perpendicular to each other at 90 degrees. Okay, they create between them at the intersection point, that is point A. They create between them 90 degrees, that is to say they are perpendicular to each other. Then, if two chords are perpendicular to each other, then the following equation will be true. 4 times capital R squared. Here, point O is the center of the circle. Point M is the point of the circle itself, therefore OM is the radius of this circle that we will define as capital R. So capital R is the radius of this circle. And 4 times, then the following equation is true, that 4 times capital R squared equals to FA squared plus AD squared plus PA squared plus AB squared. Repeat again. Chord FD intersects with chord PB at 90 degrees, that is to say the two chords are perpendicular to each other. Whenever we have two chords that are perpendicular to each other, we can implement rule number 4. This is rule number 4. It states that the following equation will be true, that 4 times r squared, r is the radius of this circle, you can see here. 4 times r squared equals to fa squared plus ad squared plus pa squared plus ab squared. So 4 times r squared, here capital R is the only missing variable. So you can find out it by solving this equation. This is true according to rule number 4. 4 times r squared equals to fa squared. Fa equals to 5, as you can see here. Therefore, fa squared equals to 5 squared, that is 25, plus ad squared. Ad equals to 18 units, as you can see here. It is given as the equation. Therefore, ad squared is 18 squared, that is 324, plus pa squared. Pa equals to 15, therefore pa squared equals to 15 squared, that is 225. Plus ab squared. Ab equals to 6, therefore ab squared equals to 6 squared, that is 36. So in conclusion, we found out that 4r squared equals to 25 plus 324 plus 225 plus 36. So 4r squared equals to 25 plus 225 is 250, and 324 plus 36 is 360. So we found out in conclusion that 4r squared equals to 250 plus 610 is 250 plus 360. It is equal to 610. So 4r squared equals to 610. We will divide this equation by 4 and we will get that r squared equals to 610 over 4. R squared equals to 610 over 4. We will take a root out of this equation and we will get that r equals to the square root of 610 over 4. So r equals to the square root of 610 and the square root of 4 is 2. So in conclusion, we found out that the radius of this circle, the radius that we are looking for, that is to say capital R, this radius, it is equal to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. So we finished with the second method. In the next step, I will summarize the lecture. We'll start with the first method. So in the drawing we have a circle. The center of this circle is at this point O. Here line segment AB equals to 6 units in its length. Line segment AD, this line segment, equals to 18 units. Line segment BC, this line segment, equals to 13 units in its length. This angle BAD equals to 90 degrees, and also this angle ABC, it is also equal to 90 degrees. And our mission is to find out the radius of this circle. This is to say, to find out the value of capital R. So in the first step, we made a construction from point C. This is point C. We draw perpendicular on AD. This is AD. So that is to say this angle equals 90 degrees and this angle also equals to 90 degrees according to our construction. And we define the touching point of the perpendicular for point C and AD as E. Okay. Here we have, by doing this construction, we created here quadrilateral ABCE. This is quadrilateral ABCE. Again, this is quadrilateral ABCE. Inside quadrilateral ABEC, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So 270 degrees plus the missing angle must be equal to 460 degrees, therefore the missing angle equals to 90 degrees. So we actually found out that inside quadrilateral ABCE we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral ABCE as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle ABCE, AB must be equal to EC. It is given us the equation that AB equals to 6, therefore EC must be also equal to 6 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that in rectangle ABCE, BC must be equal to AE, but BC equals to 13 units according to what is given us in the equation, therefore AE must be also equal to 13 units. And what is the length of line segment ED? From the drawing it is very easy to see that ED equals to AD minus AE. AD equals to 8 units, AD equals to 18 units, this is given us the equation. AE equals to 13 units according to what we have already found out. Therefore, ED equals to 18 minus 13, that is 5. So we found out that ED equals to 5 units. In the next step, we join points D and C together by a straight line. In this way, we actually created the green small triangle DCE. We implemented the Pythagoras theorem on the green small triangle DCE. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. The hypotenuse in this small right triangle is DC, therefore the square of the hypotenuse is DC square, and it must be equal to EC square plus ED square. So DC square equals to EC square plus ED square. So DC square equals to EC square. EC equals to 6, therefore EC square equals to 6 square, that is 36, plus ED square. ED equals to 5, therefore ED square equals to 5 square, that is 25. So in conclusion, we found out that DC square equals to 36 plus 25. That is to say, DC square equals to 36 plus 25 is 61. We took a root out of this equation and found out that DC equals to the square root of 61. Here the hypotenuse DC equals to the square root of 61. Then we joined points B and D together by a straight line. By joining points B and D, we created here the right triangle BAD. When we actually implemented the Pythagoras theorem on this right triangle ABD or BAD, according to the Pythagoras theorem in the right triangle ABD, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is BD, therefore the square of the hypotenuse is BD square. BD square, it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AB square plus AD square. BD square equals to AB square plus AD square. AB equals to 6, therefore AB square equals to 6 squared, that is 36. AD equals to 18 according to what is given as the question. Therefore, AD squared equals to 18 squared, this is 324. In conclusion, we found out that BD squared equals to 36 plus 324. 36 plus 324 is 360. So in conclusion, we found out that BD squared, that is the square of the hypotenuse, equals to 360. We can substitute 360 by 36 times 10. So we did it, and we got that BD squared equals to 36 times 10. We took out all of this equation and found out that BD equals to the square root of 36 times 10. The square root of 36 is 6, so we can take out 36, we can take it from the root, out of the root, and we write it instead of the square root of 36, it is equal to 6. Inside the root we left only with square root with 10. So BD, that is the hypotenuse, equals to 6 times square root of 10. Here we found out that the hypotenuse BD of the right triangle ABD equals to 6 times square root of 10 units. In the next step, we actually calculated the area of the green triangle BDC. This green triangle BDC. Okay. We know that the area of any triangle equals to the base of the triangle times the height to the base over 2. I must emphasize that the height to the base must create 90 degrees with the base. Okay, we choose the base of the green triangle BDC as BC. So here the base is BC times the height over 2. Again, the height must create 90 degrees with the base. So from point D, we draw perpendicular on the extended BC. So this again equals 90 degrees and this again equals 90 degrees according to our construction. So DF, we define the touching point of the perpendicular from point D on the extended BC as F. And DF is the height. Okay, the DF is the height to the base. And here, we created here quadrilateral ABDF. Inside this quadrilateral ABDF, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. And therefore, quadrilateral ABDF that has 4 right angles related as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to DF. Repeat again. Quadrilateral ABDF is a rectangle because it has 4 right angles, and we know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to DF. But it is given us the question that AB equals to 6 units. So we can write here that AB equals to 6, and from this equation 6 equals to AB equals to DF, we will derive that DF is also equals to 6. So we actually found out that DF, that is the height of the green triangle BDC, is equal to 6 units in its length. Now we can find out the area of the green triangle. The area of the green triangle equals to the base of the triangle, the green triangle BDC, and we know that the base BC equals to 13 units times the height to the base is equal to 6 units over 2. 6 over 2 is 3, and 3 times 13 is 39. So in conclusion, we found out that the area of this green triangle BDC equals to 39 square units. Okay. In the next step, I presented to you a new rule number 1, and we implemented rule number 1 in our drawing. Rule number 1 is true in any circle, so here this circle could be any circle. If we have in this circle triangle ABC that is blocked by the circle, why it is blocked by circle? Because of the fact that all the 3 vertices of the circle ABC touching the circle This vertex touches the circle at point A, this vertex touches the circle at point B, and this vertex touches the circle at point C. Only if all the three vertices touching the circles at any point, we can say that the triangle is blocked by the circle. Otherwise, the triangle is not blocked by the circle. Okay, in this case, all the three vertices touching the circle, therefore, the circle and the triangle is blocked by the circle. So here, triangle ABC is blocked by this circle. We know that the length of side AB is A units, the length of side AC equals to 3 units in its length, and side BC equals to B units in its length, and the radius of this circle equals to capital R. Here OM equals to capital R. So whenever you have a triangle that is blocked by a circle, you can find the radius of this circle. And the radius of the circle that blocks a triangle will be equal to the multiplication of the side lengths of the triangle by each other over 4 times the area of the triangle that is blocked by the circle. That is to say, A times B times C is the multiplication of the side lengths of the triangle ABC by each other over 4 times the area of triangle ABC. The squared bracket is the sign for the area. Okay, so we can implement rule number 1 in our drawing. Why? Because in our drawing, we have the green triangle DBC is blocked by this circle. Why? Because all the 3 vertices of the green triangle touching the circle. Here, this vertex touches the circle at point B, this vertex touches the circle at point C, and finally this vertex of the green triangle BDC touches the circle at point D. Therefore, it is absolutely true to say that the green triangle BDC is blocked by this circle. And we defined the radius of this circle, OM, it is equal to capital R. Therefore, because of the fact that this circle blocks the green triangle, we can implement here rule number 1. Okay, and according to rule number 1, again I repeat again that the green triangle BDC is blocked by a circle, therefore we can implement rule number 1. According to rule number 1, the radius of the circle, the radius of this circle that blocks the green triangle BDC will be equal to the multiplication of the side lengths of the triangle by each other. That is to say, it is BC times CD plus times DB. BC times DC times BD over 4 times the area of triangle BDC. Over 4 times the area of the green triangle BDC. BC equals to 13 units, DC equals to the square root of 16 units, and BD equals to 6 times square root of 10 units over 4 times the area of triangle BDC. And we have already found out that the area of the green triangle BDC equals to 39 square units. So in conclusion, we found out that the radius that we are looking for, that is to say the radius of this circle, equals to this expression. Here we actually simplified this expression by dividing both the numerator and the denominator of this expression by 13. Here 13 over 13 is 1, so 13 will get cancelled, and in the denominator we left only with square root of 61 times square root of 10 times 6. In the denominator we have 4 times 39. And so 39 over 13 is 3. So in total, in the denominator we left only with 4 times 3. So the radius of the circle equals to the square root of 61 times square root of 10 times 6 over 4 times 3. 4 times 3 in the denominator is 13, is 12. 4 times 3 is 12. In the numerator we have the square root of 61 times square root of 10 times square root of 6. Okay, so we divided both the numerator and the denominator of this expression by 6. 6 over 6 is 1, so we left only with, in the numerator with square root of 61 times square root of 10, and 12 over 2 is, 12 over 6 is 2. So in conclusion, we found out that the radius of this circle, the radius that we are looking for, equals to the square root of 61 times square root of 10 over 2. According to the algebraic identity that the square root of a times square root of b equals to the square root of a times b, we get that the square root of 61 times square root of 10 equals to the square root of 61 times 10, all divided by 2. 61 times 10 is 610, so in conclusion I found out that the radius of this circle is equal to either the square root of 610 over 2 units, so in terms of numbers, it is equal to 12.349 units. So finished with the first method. Then I presented to you the second method. The second method to find out the radius of this circle. Here we did the things that we did already in the first method, that is to say from point C we draw perpendicular on AD, this angle equals 90 degrees and this angle equals 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AD as E. Here, by doing this construction, we created quadrilateral ABEC that has 3 right angles, therefore the fourth angle must be equal to 90 degrees, and therefore quadrilateral ABEC is a rectangle because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other, that is to say AB equals to EC, but AB equals to 6, therefore EC also equals to 6. Likewise, according to the sum rule that the opposite sides of a rectangle are equal to each other, we will get that BC equals to AE, but BC equals to 13 units, therefore AE also equals to 13 units. And AD equals to AD minus AE, that is to say it is 18 minus 13, that is 5. Then, so until now we did all the things that we already done in the first method. And then here from point O we draw perpendicular, from point O that is the center of the circle of course we draw perpendicular on chord BC. So this angle equals 90 degrees and this angle equals 90 degrees according to our construction. We define the touching point of the perpendicular from point O and BC as capital N. And we define the touching point of the perpendicular from point O and E as capital M. Then I presented to you rule number 1 and we implemented rule number 1 in our drawing. According to rule number 1, the perpendicular from the center of the circle, that is to say from point O, towards any chord. Here, chord BC could be any chord. Bisect the chords. That is to say, it divides chords BC into 2 halves. The first half is BM and the second half is MC. That is to say, BM equals to MC. Okay. Again, the perpendicular OM from the center of the circle, that is to say from point O, bisects the chord BC. Chord BC could be any chord. That is to say BM equals to MC. Okay, this is rule number 2. We actually can implement rule number 2 in our drawing. Why? Because in our drawing, from the center of this circle, that is to say from point O, we have perpendicular ON that bisects chord BC. Again, because of the fact that we have the perpendicular ON from the center of the circle, that is to say from point O, so here the perpendicular ON bisects chord BC. That is to say, BN equals to NC. According to rule number 2, the perpendicular ON bisects chord BC. That is to say, BN equals to NC. BN equals to NC according to rule number 2. Again, because of the fact that ON is perpendicular to BC and ON exists from the center of the circle, that is to say from point O, the perpendicular BC, it is also bisects chord BC. That is to say BN equals to NC according to rule number 2. Then we focus on quadrilateral ABMN. Inside quadrilateral ABMN, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees, and therefore quadrilateral ABMN is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, AM equals to BN. Okay, here, quadrilateral ABMN is a rectangle because it has 4 right angles, and we know that the opposite sides of a rectangle are equal to each other. Therefore, AM equals to BN. Likewise, we focus on quadrilateral MNEC. This quadrilateral, we have 1, 2, 3 right angles. Okay, and therefore the fourth angle must be also equal to 90 degrees. And actually in quadrilateral MNEC we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, so we relate quadrilateral MNEC as a rectangle. If in the end, quadrilateral MNEC is a rectangle because it has 4 right angles. But we know that the opposite sides of a rectangle are equal to each other. That is to say, ME equals to NC. ME equals to NC. So we can summarize what we did until now. We have already found out that BN equals to NC according to rule number 2. But BN, it is also equal to AM according to this formula. So we can write here that BN equals to AM. And we have already found out that NC it is also equals to ME. So we can write here that NC equals to ME. From this long equation, AM equals to BN equals to NC equals to ME, we will derive that AM equals to ME. Here, AM, line segment AM equals to line segment ME. Okay, then we actually extended line segment DA until it touches the circle at point F. In this way, by this construction, actually created chord FD. This is called FD. And then we implemented the old rule number 2 in our drawing. According to the old rule number 2, that is drawn in any circle, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OB. CO times OD. Again, AO times OB equals to CO times OD. We actually can implement rule number 2 in our drawing, because in our drawing we have, before that, actually, we extended chord FA, we extended chord DA until it touches the circle at point F. Okay? And then we have here from the center of the circle, we have perpendicular to BC. But here ON is perpendicular, so ON is perpendicular, it is absolutely a straight line. So if you focus on the upper side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of ON at point M? We have this angle that is equal to 90 degrees plus the missing angle. In total they must be equal to 90 degrees. Therefore the missing angle must be equal to 90 degrees. Likewise, if you focus on the lower side of ON at point M, here the sum of the angles must be equal to 180 degrees according to the sum rule. So which angles we have on the lower side of ON at point M? We have this angle that is equal to 90 degrees plus the missing angle. In total they must be equal to 180 degrees. Therefore the missing angle must be also equal to 90 degrees. So we have line segment OM that is perpendicular to chord FD. Why? Because this angle equals to 90 degrees and this angle equals to 90 degrees. Therefore, we can implement here rule number 2. Because of the fact that line segment OM is perpendicular to chord FD, we can implement here rule number 2. According to rule number 2, the perpendicular OM that is exists from the center of the circle bisects chord FD. That is to say, FM equals to MD. Okay, according to rule number 2, because of the fact that from the center of the circle perpendicular ON is perpendicular to chord FD, according to rule number 2, it bisects chord FD, that is to say FM equals to MD. Because of the fact that OM bisects chord FD, it means that FM equals to MD. According to rule number 2. So what is the value of FM? The value of FM, it is very easy to say from the drawing that FM equals to FA plus AM. So we can substitute FM by FA plus AM. And it is equal to MD. What is the value of MD? MD equals to ME plus ED. So we can substitute MD by ME plus MD. Here we substitute MD by ME plus ED. So those two expressions are equal to each other. But we have already found out that AM equals to ME. So those two line segments are equal to each other, therefore we can cancel them. And we're left only with FA that is equal to ED. FA equals to ED according to this equation. FA equals to ED. But we have already found out that ED equals to 5 units. If ED equals to 5 and from this equation FA equals to ED equals to 5, we will derive that FA is also equals to 5 units. FA equals to 5 units. Okay? Now we actually extend that side BA until it touches the circle at point P. Okay? So then I presented to you the old rule number 2, and we implemented rule number 2, the old rule number 2 in our drawing. According to the old rule number 2, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. So actually we can implement rule number 2 in our drawing. Why? Because in our drawing we have chord FD that intersects with chord PB at point A. Repeat again. Chord FD intersects with chord PB at point A. Therefore, we can implement the old rule number 2. According to the old rule number 2, we get that FA times AD equals to PA times AB. Again, FA times AD equals to PA times AB. According to the old rule number 2, FA times AD equals to PA times AB. FA equals to 5. AD equals to 18. FA equals to 5. AD equals to 18. PA is the missing line segment, so we leave it as it is. And AB equals to 6, so we substitute AB by 6. In conclusion, we found out that 5 times 18 equals to PA times 6. Here we divided this equation by 6 and found out that PA equals to 5 times 18 over 6. 18 over 6 is 3, and 3 times 5 is 15. So we found out that PA equals to 15 units. Here the missing 9 segment PA equals to 15 units. Then I presented to you rule number 4, and we implemented rule number 4 in our drawing. According to rule number 4, in general, rule number 4 states that whenever you have two chords that are perpendicular to each other, you can implement here this formula. That is to say, if we have chord AB that intersects with chord CD at 90 degrees, that is to say the two chords AB and CD are perpendicular to each other. As you can see here, they create between them at the intersection point, that is point O, 90 degrees. Then you can implement, whenever you have two chords that are perpendicular to each other, you can use this formula that is actually 4r squared, and r is the radius of this circle, equals to AO squared plus OB squared plus CO squared plus OD squared. Okay? So we actually can implement rule number 4 in our drawing. Why? Because in our drawing we have chord FD that intersects with chord PB at 90 degrees. That is to say the two chords are perpendicular to each other, therefore we can implement here rule number 2. The radius of this circle is equal to capital R, and according to rule number 2, 4 times R squared equals to FA squared plus AD squared plus PA squared plus AB squared. I'll repeat again. Because of the fact that chord FD intersects with chord PB at 90 degrees, therefore that is to say they are perpendicular to each other. The intersection point occurs at point A. Then you can implement here rule number 4. According to rule number 4, we get that 4R squared equals to FA squared plus AD squared plus PA squared plus AB squared. Okay? Here, FA equals to 5, therefore FA squared equals to 5 squared, that is 25. AD equals to 8 units, therefore AD squared equals to 324. Plus PA squared. PA equals to 15, therefore PA squared is 15 squared, that is 225. Plus AB squared. AB equals to 6, therefore AB squared equals to 6 squared, that is 36. So 4R squared equals to 25 plus 225 is 250, and 324 plus 36 is 360. So in conclusion, we found out that 4R squared equals to 250 plus 360. 250 plus 360 is 610. So in conclusion, we found out that 4R squared equals to 610. We divided this equation by 4 and we found out that R squared equals to 610 over 4. Here we took a root out of this equation and found out that R equals to the square root of 610 over 4. That is to say, R equals to the square root of 610, and the square root of 4 is 2. So in conclusion, we found out that R equals to the square root of 610 over 2 units. So the radius of this circle equals to either the square root of 610 units over 2, it is equal to the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. Okay, thank you very much.